Okay, so in this video, we will discuss rate of change. I've already written what you have to know. So essentially, the rate of change is the ratio delta y over delta x, which the average rate of change, this is basically the average rate of change over the interval delta x. So we have this delta y could be written as y2 minus y1. In the same way, delta x could be written as x2 minus x1. And y2 could be rewritten as f of x2. And y1, it could be rewritten as f of x1. So as delta x approaches 0, the ratio is approaching a limiting value, which is defined as the rate of change of y, corresponding to the given value of x, or this is called the instantaneous rate of change. So don't dwell too much on the theory. Let's head immediately to the practice question. So the equation that I have here, it basically corresponds to, it represents the supply for a certain brand of candy. So talk about supply chain. X is the price of the candy. So we are tasked to find the rate of change of the supply per peso change in the price. So there are two scenarios. So when the price increases from 1 peso to 2 pesos. And for the second scenario, when the price is 1 peso. So how do we solve? How do we look for the rate of change of the supply per peso change in the price? So in this kind of question, basically what we do is, so we have a numerator and denominator, and we have to find the derivative of both of them. What do I mean by that? So that's the derivative. You just copy at the bottom. So what takes the, how do I say this? So when the price changes from 1 peso to 2 pesos, delta S over delta X, S2 minus S1 over X2 minus X1. We have to identify first S2, that is when the price is 2 pesos already. So 2 raised to 4 minus 2 raised to 3 plus 2 raised to 2 minus 2. If we further simplify, 16 minus 8 plus 4 minus 2, 20, 10. So the rate of change is going to be 10 units per peso, or basically 10 candies per peso. when the price is 1 pesos, we want to look for the instantaneous change in supply. Okay, ds over dx is what we have to look for. So I apologize for writing this. I don't think it's important or relevant either. I'll remove this already. I think I was still experimenting on what I was supposed to do when I was making the solution paper. So this is where we find the derivative. So 4x cubed minus 3x squared plus 2x minus 1. Then we substitute x as 1. 4 times 1 cubed minus 3 times 1 squared plus 2 times 1 minus 1. So ds over dx is 2. Let's answer another practice question. So suppose we have a right circular cylinder that has a constant height of 10 meters. So the volume in meters cubed, so that's going to be the volume of the right circular cylinder. What's the formula? Pi r squared h, right? We find the rate of change of the volume with respect to r. If r changes, so we have 3 scenarios. If the radius changes from 5 to 5.1, second scenario from 5 to 5.4 meters, and at radius equal to 5 meters. Okay, so this is what we have to look for in terms of these 3 scenarios. Now, how do we start? So delta V over delta R. R2, this is R2, this is R1. So pi R squared R2 squared H minus pi R1 squared H. Divided by R2 minus R1. So how did I write this? So at the top is the volume, right? So the formula, you write it down, but specifically here it's gonna be about the second radius, which is 5.1, and the next one over here is about the first radius, 5. So pi 5.1 squared h minus pi 5 squared h divided by 5.1 minus 5. So I believe we can factor something here. So by the way, let's substitute height also. 10, 10. So we can substitute, we can factor 10 pi. So what we have left is 5.1 squared minus 5 squared. So we can cancel, as you can see. So 10 pi times quantity 5, let's just make this 10.1. 10.1 times 10 is going to be 101. So this is our answer for the first part. What is going to be the unit? So volume's unit is meters cubed. For the radius, it is also meters. So we write it like that. And same thing. We do the same way for solving for number 2. Pi R2 is 5.4. I'll substitute the values directly already. For the height, it's 10, right? So 10. Below, R2 minus R1. We can factor something, 10 pi. 5.4 squared minus 5 squared. 5.4 minus 5. We can factor so we have 10 pi times the quantity, or we can just simplify already. It's going to be 10.4. So we have 104 pi meters cubed over meters. So that's the answer for number 2. For number 3, at radius is equal to 5 meters, essentially we want to look for dV over dr. So we find the derivative first of the formula, the volume of the right cylinder. So how do we do that? Both R and H are variables. The only constant is pi, so we put pi at the left side. And then we apply product rule. So 2R times H plus R squared times 0. So why is H equal to 0 when we find its derivative? Since our expression here is with respect to R, that basically means all other letters in an expression such as this is considered a constant. So H here is a constant. Similarly, this way of thinking is going to be needed when solving for partial derivatives. That's going to be a future lesson, so keep in mind. So continuing, we have therefore 2 pi r h, and when we substitute r as 5, 2 pi 5, oh, don't forget the height also. The height is said to be 10, so 50, 100. The answer is 100 pi meters cubed over meters. Okay. What other practice questions do we have? One more example before we move on to related rates. So we are tasked to find the rate of change of the area of an equilateral triangle. So note, we are only dealing with a 2D figure, not a 3D. So the area of an equilateral triangle is equal to what? So note the formula if you haven't, if you don't know it yet, or if you forgot about it. It's square root of 3 divided by 4 times s squared. So again, I'll read the instructions. You find the rate of change of the area of an equilateral triangle with respect to the side. So dA over ds with respect to the side, so over ds. We have two scenarios. When the side is equal to 4 feet, and for the second scenario, when the side changes from 4 to 4.4 feet. So this is going to be S2, 4 is going to be S1. So what do we do now? dA over ds, we find the derivative, right, coming from the original formula. So square root of 3 over 4 is a constant. Leave that at the left side. Derive, so bring down 2 and then s raised to 1, or just 2s. Now we substitute s as 4. So square root of 3 over 4 times 2 times 4 cancel to square root of 3. That's the answer for number 1. For number 2, since we have S1, S2, we have delta A over delta S. And we don't find the derivative of this, we just substitute. So S, let me show you. Square root of 3 over 4 times S2 raised to 2 minus square root of 3 over 4 S1, S2 divided by S2 minus S1. So square root of 3 over 4, S2 is 4.4 squared, and then square root of 3 over 4 times 4 squared. Just substitute, basically. Now, at this point, we can factor square root of 3 over 4. So we have something like this. Further simplify. Then we can cancel something. 4.4 plus 8.4 is what? 8 point. I just said the answer. 8.4. This is, in other words, 2.1 square root of 3 feet cubed per feet. So that is the answer for number 2. So those are the rates of change of the area of an equilateral triangle with respect to the side based on the specified scenarios. So, what else? Okay, actually, we're not going to start related rates yet. Let's have one more example. So suppose that we have a right circular cone, and it has a constant height of 10 meters. We are tasked to find the rate of change of its volume with respect to its radius when the radius is 4 meters. The unit is supposed to be meter cubed per meter. So rather, this is what we find. Now, the formula for the volume of a cone is 1 over 3 pi r squared h. So we want to find the derivative with respect to r. That means we render the h as a constant when we derive. So again, once we derive, we put the constant values at the left side, and looks like we use product rule. 2r times h plus r squared times 0. Derivative of h, assuming it's a constant, is 0. So pi over 3 2rh. I think that's it. And then we substitute the values. The radius being equal to 4 and the height being equal to 10. Fortunately, we cannot cancel anything. 80 pi over 3 is the answer. That's it. That's the final answer. That's the rate of change of its volume with respect to its radius when the radius is 4 meters. Okay. Now, let's start with related rates already. So, y is equal to f of x such that t is equal to time. And this is an independent variable. So, in calculus, when you encounter a word problem involving time, so for example, let's say there is this gallon, a container of a water container that is in the shape of a cylinder, and it has a hole somewhere, and as time passes by, its water content reduces. So as time passes, the water content reduces naturally. So problems that have that kind of scenario, we always think that it's related rates. From there, it's easier to identify how we would solve the problem. So let's see. dy over dt. So with respect to time, d f of x over dt. Same thing. So you always express f of x only as a function of one variable x. If any other variables exist in f of x, then you express those variables in terms of x. Let's have an example. So we have a rectangle, and we are given the width and height. So width is 9. 16 by 9 triangle is expanding at a rate of 6 meters squared per minute. So expanding at a rate of, since we're dealing with something related to area, so dA over dt. Over dt is always going to be basically the denominator, since we're talking about related rates. So we have a value of 6 meters squared per minute. How fast is the width of the rectangle expanding at width equal to 7 meters? Okay. 16 and 9. At width equal to 7 meters, how fast is the width of the rectangle expanding? So what are we looking for? We're basically looking for dw over dt. How fast is the width expanding over a period of time? So our formula is going to be height times width, or width times height. Same thing, just different label. We do have 16 and 9, right? So 16 over 9 is equal to the width, right? 16 by 9 width times height. This is the order. So width is to 16, height is to 9. So let's try expressing in terms of another variable. So 16h equal to 9w. H is equal to w 9 over 16. Let's use that. So the area again is equal to hw, right? But if we substitute h as w times 9 over 16, so we'll have something like this. 9 over 16 w squared is equal to a. And now we find the derivative, dA over dt. Since we already know what... sorry, give me some time to think. Okay, so once the reason why we express h in terms of w, because we are looking for dw over dt, right? So given that we have this already, once we find its derivative, so 9 over 16 2w raised to 1 times dw over dt. So this is where we find dw over dt. And earlier, it was mentioned that we have the value of dA over dt, 6, right? So 6, 9 over 16 times 2 times w. W is said to be what? 7, right? Cancel. (48) equal to 63. Divide. (21). So this is the answer. We just simplified 48 over 63. That's it for this problem. So that's how fast the width is expanding at w equal to 7 meters. Next. So we have a spherical balloon that is being filled with gas at 10 meters squared per hour. This is our dV over dt. At the instant when the surface area of the balloon is, okay, so surface area dSA over dt. The surface area of the balloon is increasing at 4 meters squared per hour. What is the radius of the balloon? So the radius is what we are looking for. And the formula for a sphere, for a sphere's volume, is 4 over 3 pi r cubed. Right? So also, the surface area of a sphere is what? So according to my answer key, it's 4 pi r squared. Now, let's derive. dV over dt is equal to 4 over 3 pi 3r squared times dr over dt. So we don't know what dr over dt is. Let's try to find the derivative first of surface area. So 4 pi 2r times dr over dt. This becomes 8 pi r dr over dt. This becomes 4 pi r squared dr over dt. What's next? This is equal to 10, right? And this one is equal to 4. Now what do we do next? We express everything in terms of, well, only in one side will dr over dt be situated. So that's what we intend to do. So we have dr over dt is equal to 10, let's say 5 over 2 pi r squared. Am I doing it right? Okay, sure. Dr over dt is equal to 1 over 2 pi r. So then we equate. Since both of them are equal to dr over dt, 5 over 2 pi r squared is equal to 1 over 2 pi r. Now, we multiply both sides by 2 pi r squared. So we have 5 equal to r. That's it. We found the radius. The radius is, what's the unit? 5 meters. The unit is in meters, so 5 meters. That's it. Sorry. Next question. Okay, so we have a cone. Oh, this is crazy. This is actually one of the hardest questions in related weights. So get ready. We're gonna answer it. Let me illustrate the 2D render of the cone. So in this scenario, basically, water is leaking at the rate of 2 feet cubed per minute. So in other words, dV over dt is equal to negative 2 feet cubed per minute. Why is it negative? From the word leaking, so decreasing volume. So through a hole in the vertex of an inverted conical reservoir of the height 6 feet. So the height is said to be 6 feet and a diameter of 4 feet at the top. So the question is, for the first, how fast is the water level changing when the reservoir is 1/8 full? And the second question is, how long will it take for the tank to be empty? So let's deal with the first question first. How fast is the water level changing when the reservoir is 1/8 full? Since the diameter is 4 feet, we already know the radius, it's 2 feet. The volume of a cone is 1/3 pi r squared h. When the tank is full, so let's just substitute the values. First, radius is 2, right? And then height is 6. 2, 8 pi. So this is the volume of the reservoir when it's full. And also, we want to express r as a function of h. We have the radius as 2 and the height as 6, so r over h. 2h is equal to 6r. r is equal to 1 over 3h. We'll use this in a while. Also, since this is the full value, at 1 over 8 capacity, so volume is equal to 8 pi, right? And we multiply it by 1 over 8. So it just so happens that these two are the same number. It's not a coincidence. So the volume at 1/8 capacity is equal to pi. And in the volume, wherein the capacity is just 1 over 8 full, so pi is equal to 1 over 3 pi r squared h. This is the volume formula. Don't be confused. And from here, we substitute the radius so that we only have, in terms of, basically you don't write h anymore. Oh wait, no, it's actually the other way around. So everything will be involving the variable h. Let me show you. So 1 over 3 pi r is 1/3 h, right? And then squared h. Simplify. So we will have pi over 3 h cubed 1 over 9. So we have what? Pi h cubed over 27. 27 pi equal to 27 h3. Solve for h. 27 equal to h cubed. H is therefore equal to 3. So we found the height. What do we do next? dV over dt. So again, the formula of the volume of a cone is 1 over 3 pi r squared h. Find the derivative. And of course, we use this. So there's no more radius in the volume formula. It's all height. That's exactly what we want. So let's just simplify first before we start deriving. Okay, now we start deriving. Pi over 27 dV over dt is what? -2, right? So -2 our height is what? 3, right? So negative 54 over pi times 3 raised to 2. 27, negative 2 pi. That is our answer, feet per minute. Okay? So that's how fast the water level changes. We only answered letter A. What about letter B? How long will it take for the tank to be empty? So what are we talking about here? Again, the volume of a full tank is equal to 8 pi, right? So coming from full to empty, basically what we're being asked is how long. So time. Time, in the context of our problem, is equal to the volume divided by dv over dt. So in other words, it is 8 pi divided by dv over dt, which is said to be negative 2, right? So negative 2, don't forget the units. So what we have is negative 4 pi minutes. Sorry, actually, so we have a negative value, right? But when it comes to time, this negative sign only means that the container is losing volume. But actually, we disregard the negative sign when the answer that we're trying to find is time. So in this scenario specifically, we disregard the negative sign anymore. So basically, it's going to be 4. You can't say that the answer is negative 4 pi minutes. That's just what I want to say. So that is it. How many more practice questions? 1, 2, 2 more. 2 more. Okay, so this time it's going to be a triangle. A kite is 40 feet high with a 50 feet of cord that's out. If the kite moves horizontally at 5 feet per minute directly away from the boy flying it, how fast is the cord being paid out? Or I think the word is supposed to be being laid out. Actually, no. Being paid out. How fast is the cord being paid out means how fast is the cord of the kite being pulled away from the boy. So dx over dt is equal to 5 feet per minute. So 50 feet of cord out. This is going to be the 50 feet over hypotenuse. The boy is right here. The kite is right there. This is the cord. So how fast is the cord being paid out? Time is definitely involved because we have minute. And so we are looking for ds over dt. But what is the s? Side, I guess, because we don't have the value of this. Actually, let's look for it. Let's say this is A, this is B, this is C. So using the Pythagorean theorem, C is equal to the square root of A squared plus 40 squared. C is 50, right? Actually, uh, 50 squared is 2500. 40 squared is 1600. So this is going to be 900 or 30 squared. Therefore, A is equal to 30. So let's move on now to finding ds over dt, or basically deriving s is equal to x squared plus 40 squared. One half x squared plus 40 squared raised to negative 1 half times 2x times dx over dt. 2x over 2 times the square root of x squared plus 1/6. Dx over dt, as stated earlier, is equal to 5 feet per minute, right? So 5. Cancel the 2. We identified x earlier, or a, in other words, as 30. So x here will become 30. 30 times 5. Wait, x is also 30. So 30 squared is 900 plus 1/6, 20 to 500. 50. Yeah, 50. 30 times 5, just leave it as is. We can cancel something. So ds over dt is equal to 3 feet per minute. So that is how fast the kite is being pulled away from the buoy. That's what represents this value. Last question. So wheat is poured on the ground at the rate of 8 liters per minute. So essentially this wheat, it forms a cone because it is being poured on the ground. So the rate 8 liters per minute, this is going to be dv over dt. So the pile forms a cone whose altitude is always, or in other words the height, is always 2/3 of the radius. Find the rate at which the altitude is increasing when the altitude is 1.5 meters. Let's find the radius with that information. Oh, okay. So the radius is 9 over 4. Wait. That's more like it. 2.25. Okay. Rather, let's just stick with this as our radius. So now that we have the radius and height, By the way, this is a cone, so volume is pi r squared h, 1 over 3. And the radius is 9 over 4. The height is what? 2 over 3 times 9 over 4. 3 over 2. Okay? 9 over 4 h equal to 3 over 2 r. Let's express r in terms of h instead. 2r is equal to 3h. R is equal to 3 over 2h. So, using that, volume is equal to 1/3 pi r squared h. Substitute. Okay. So that is our volume now. Only expressed in terms of height, no more radius. Now, we find its derivative. What we were given earlier is its value. From there, we find dH over dt eventually. Let me show you. So 3 pi over 4 is a constant. Set it aside. 3h squared and then dH over dt. We know what the height value is. We also know dV over dt, right? So dV over dt is 8. By the way, let me just tell you this. Liters per minute, this could be also written as dm cubed per minute. Liter and dm cubed are the same. So 3 pi over 4 times 3 times height, which is, what is the height? (1.5) or 3 over 2. Is it? I think there's something with the units. Okay, so 8 liters per minute, decimeters, right? That is in terms of decimeters. How about our height? Our height is 1.5 meters. Convert it to decimeters. So that's 15 dm. I think that's what's up. 15 squared times dH over dt. And then don't forget 8. Multiply both sides by 4. Okay. Next is two to 5 times 9. 2025. So that's the answer already. dm per minute. dH over dt again means it is the rate at which the altitude is increasing when the altitude is 1.5 meters. So height, altitude. Okay, that is finished. We are done with related rates. Next video will be about optimization, the final boss. Arguably one of the hardest topics in differential calculus. I mean, it only takes you the moment that when you don't understand the question, so that bears the possibility of you screwing up the test, because if you don't get the question, you can't solve it. If you can't solve it, you don't get much partial points. So you need to be resourceful. That's it for this video. Thanks for watching.